This is the first of two videos on step 3, and this is where we're going to determine if the test statistic that we calculated on step 2 is an unusual value. So I'm going to open up the document, and there are going to be three ways for us to make this determination. There are three approaches. First is going to be a critical value approach, which is a traditional approach, and we're going to discuss that in this video. And then there's the p-value approach, and that will be in the second video. Then there is a third, which is called the confidence interval approach, and the confidence interval approach is not used as much, and we're only going to introduce that when we talk about the chapter 3 material leading into test 3. So for now, we're going to be talking about the critical value approach. Now, this video and the next one as well is going to show you the what and the why of doing these approaches to determine if the test statistic is unusual or not, or rather unlikely. But we're going to leave the why, or not the why, but the how we determine this, how we do this in both the critical value approach and the p-value approach. We're going to leave that until we talk about the individual hypothesis tests by themselves. We'll do a separate video on each of them, short video, and we'll leave the how to that, how we do things, how we use the calculator in order to do this, and tables as well. So let's first talk about the critical value approach, the traditional approach. And the first thing we're going to need to know is we need to know what alpha is, the but the significance level. Remember, that is the unlikely probability. We need to know what alpha is, and we also need to know what relationship we have in the alternate hypothesis. Remember what the alternate hypothesis, as we saw when we looked at that table in step 1, it tells us whether it is a left-tailed test, in other words, would the unusual values be on the left side of the mean, or if it's a right-tailed test, would the unusual values of the test statistic be on the right side of the mean. I believe I say that right? Left tail on the left side of the mean, right tail on the right side of the mean, and two tail whether it is on one or the other side of the mean. Okay, now, so let's look at how we would start out. First, we define alpha. We know what alpha is, that small probability, and H1 tells us whether we're going to worry about the left side, right side, or both sides. And what we're going to do is draw a little sketch. And that sketch is going to have a horizontal line. And that line is values of the test statistic. If we're talking about a test of proportion, that would be values of Z. And the mean of Z would be in the middle here, 0. If we were talking about test of the mean, that would be values, the numbers along here would be values of T. And the mean of T right in the middle would be 0. And if we're talking about chi-squared, I don't have a chi-squared picture here, but remember, chi-squared starts at 0, and the mean is a sample size minus 1. So we've got our point of reference in that mean. And but values of chi-squared would be along the horizontal axis. Excuse me. Then we sketched, and then we sketched the curve above that axis. And this basically is the density function curve, and it allows us to find areas underneath the curve between start and stop points for the test statistic. And we did this in chapter 6. And it allows us to identify alpha as the small rejection, basically, or unlikely probability. So once we've got our curve set up, we need to plot some things on it. A horizontal line with the mean marked. We've got the curve above the horizontal line, the test statistic axis. And other things we're going to plot on here are going to be the critical values. If H1 is less than, then we'll have a single critical value on the left. And that critical value will define, or will separate all the values of the random variable into those for which we will fail to reject, which are closer to the mean and beyond on the other side, and those for which we will reject. So we would have any test statistic value over here would cause us to reject the null hypothesis. And remember, the null hypothesis is the assumed value of the test of the parameter in the population. And that area underneath the curve, that's the critical value, sets up an area underneath the curve to the left, since it's left tail, that is equal to alpha. So this area right here is that unusual probability. If it's a right-tailed test, then we would, I'm sorry, a two-tailed test. If it's a two-tailed test, then we have to have two critical values, one on each side of the mean. So we would plot both of those as well as the mean, and we would find areas underneath the curve farther away from the mean than the test statistic, the critical value on the right and on the left. And alpha is the total unusual or unlikely probability. And so what we're going to do is split that unusual probability or unlikely probability into two parts. The area underneath the curve to the right of the right side critical value is going to be half of alpha. The probability of getting a test statistic greater than the critical value there underneath or under the assumed value is going to be half of alpha. And then on the left, half of alpha to the left of the left side critical value. And so these two critical values split all the possible test statistic values into those for which we will reject, which is farther than the critical value on the left and farther from the critical value on the right, farther from that critical value than the mean, farther from the mean than the critical value on the right, farther from the mean than that critical value on the left. Then we have if H1, the alternate hypothesis is greater than. It's a right-tailed test, so we'll have one critical value on the right. That critical value will split all the test statistic values into those for which we'll fail to reject and those for which we will reject. If we get a test statistic value that is farther from the mean than the critical value on the right, we will reject. And the area underneath the curve to the right of that critical value on the right is equal to that unlikely probability. So, like I said, this is what we're doing and why we're doing it, because we're trying to find the values of the test statistic that are going to cause us to reject. And we'll find a critical value, and we need to make sure it's on the right side and that the area farther from the mean than the critical value is equal to a certain probability defined by alpha. Okay, so with that, and like I said, that's the what and why, but now the how. How do we find the critical value? There, in this table right here, you'll see it has how we're going to do it, and we'll reserve discussion of those until we get to individual hypothesis tests, okay? So let's now look at some practice problems and just look at how we would, or what we would do for each one of those in terms of critical value. So I'm going to stop sharing this and go over to here, set this up, and go back and share again. And, oops. And you should be seeing the hypothesis test practice solutions. And let's look at the first problem. Again, we know that the claim was the mean less than 70, and alternate hypothesis then was that the mean was less than 70, same as the claim, because the claim didn't have an equal part. And so this is a left-tailed test, okay? Because we have a less than probability in H1, which means we need to find one critical value on the left. And that critical value will split all possible test statistic values into those for which we will reject on the left and those for which we will not reject to the right of the critical value. So we find that the critical value is T, again, because remember, everything along this axis is a test statistic value, including the mean, which was 0 in this case, for a T. And any value plotted along here would be a T, which means critical values are also T's. So we got T equals negative 1.717, which is over here. This is the critical value sketch. And it would be a good idea for you to, and it would help you to see what's going on if you do these sketches for critical value, and when we get to a p-value, it helps you to see what's happening here. So we've got our mean here. We've got our negative 1.717 sketched, plotted, and alpha is 0.05, so this area underneath the curve to the left of negative 1.717, the critical value, is equal to alpha. That's our unlikely probability, so that any test statistic value that is more negative than negative 1.717, farther from the mean than this critical value, would cause us to reject H0. And so what we need to do now is plot the actual test statistic that we found in step 2 and see where that is. Is it in the rejection region here, or is it in the fail to reject region? And it is in the fail to reject region, okay? So this tells us that we're going to end up rejecting H0 in our decision. So let's go look at the next one. Again, and this one is a test of standard deviation. So it's a different looking curve. But let's see what we've got here. We have that the claim was that sigma is greater than 1. It doesn't have a zero. It does not have an equals part. And therefore, the alternate is the same, sigma greater than 1. And since the relationship in H1 is greater than, it's a right-tailed test. That means we're going to have one critical value on the right. So we would have to go find that critical value, knowing alpha and knowing it's a right-tailed test. And we see that it is 70, I'm sorry, where are we here? I'm sorry, 76.154. I've already got the number written in here for a right-tailed test. And remember that 76.154 splits all of the test statistic values into numbers greater than that. And this is on the right, which means that is the rejection region, the critical region, and therefore we will reject if our test statistic is in that region. And then we plot the test statistic, and we see that it is not in that region. It is not farther from the mean than the critical value of 76.154. It was 72, and it is less than. So that means that we will fail to reject when we get to the decision. So this tells us that our test statistic is not unlikely. And let's go to the next one. We see that, and by the way, the area underneath the curve to the right of the critical value is going to be equal to alpha. And in this case, alpha was 0.01, okay? 0.01, not 0.05. That's why that's such a small area out there. And then here we have another test of standard deviation. We see that the alternate hypothesis is greater than, therefore it's again a right-tailed test. So we need one critical value on the right. We will go find that, and we'll talk about again, I said we'd talk about that later. We see that the critical value is 36.415. So we draw our sketch. Remember, it starts at 0. The mean is a sample size minus 1, which in this case would be 24. And we plot the critical value that we found, 36.415. And the area to the right, since it's a right-tailed test, is going to be equal to alpha, which in this case is 0.05. And it's hard to see here, but the test statistic that we found was 36.507, and 36.507 is going to be just to the right of 36.415. It's bigger than 36.415 on the right side. Therefore, it's farther away from the mean than the critical value. And therefore, our test statistic is going to be unlikely to occur under the assumption. Let's look at the next one. And our alternate hypothesis is not equal. And that means it's a two-tailed test. So we're going to have to find two, and by the way, this is a test of the mean. We're going to have to find two critical values, one on each side of the mean. And those two critical values are going to split the test statistic values into three regions. On the left, if we find a test statistic that is farther to the left of the left critical value, and or on the right, if we find a test statistic that is farther to the right of the right critical value, it would be unlikely. And in between those two things would be the values of the test statistic that were not unlikely. And remember, for a t, because this is t equals negative 4.733, and both of these critical values are t. And by the way, the total area underneath the curve to the left of the left critical value, to the right of the right critical value, those things have to total up to 0.05. So basically, half the area is in each of those regions, 0.025. And the fact that it has to be 0.025 is that's what we use to find what the critical values are. Okay, so we plot our test statistic, and our test statistic is negative 4.733, and that is way out here. And so it is in the rejection region or critical region over here. It is farther away from the critical value on the left than the mean, which means it is in the unusual rejection region. All right, the next two, we're talking about, let's look at the relationship. It is less than, alpha is 0.05. Relationship in H1 is less than, with making it a left-tailed test, which means, and we're also, it's a test of proportion. So we know which, when we're finding the critical value, we know which function on the calculator or which table we're going to use to do that. So we need one critical value on the left for less than. And we find that to be, it's Z, because we're talking about test of proportion, it's negative 1.645. And so we draw our curve, draw our horizontal axis for test statistic values, draw the normal curve above that. The mean is 0. We plot the critical value on the left, and numbers farther away from the mean than the critical value out here are going to be unusual or unlikely or unusual. And the area underneath that curve is 0.05. So if we find a critical value, a test statistic value that is farther to the left than the critical value of negative 1.645, if our test statistic is farther to the left, it's unusual or unlikely. And we plot that value, negative 1.46, that we found in step 2, and sure enough, it is not in the rejection or unusual or critical region, okay, underneath the shaded part of the curve. So it's not unlikely. Then let's look at the last one. We have, again, in H1, it is a test of proportion, and it is not equal, meaning it is a two-tailed test, okay? So we're going to, and alpha is 0.05 again. Two-tailed test means we need two critical values, one on either side of the mean. And we go to find those, and we find that the one on the left is negative 1.96, and the one on the right is positive 1.96. So we draw our line for test statistic values. We would plot the 0 for the mean, so we have a point of reference. And we plot 1.96 on the right and draw a sketch or shade in underneath the curve to the right of 1.96. Plot negative 1.96 on the left and shade in underneath the curve farther to the left, farther from the mean than negative 1.96. So any value of test statistic that happens to be bigger than 1.96 or less than negative 1.96 is going to cause us to say that the test statistic is unusual. So we need to plot it. Our test statistic from step 2 was Z equals negative 2.19. So it's on the left. We plot it, and we find that it is farther from the mean than the left critical value of negative 1.96, putting it in this rejection region. Therefore, we found that the test statistic Z equals negative 2.19 is unlikely to occur under the assumed value for P. And that covers the what and why of finding critical values, doing a critical value approach to determining if a test statistic is unlikely. So let's stop the sharing and go back, and we'll stop this recording.